So in this video we're going to have a look through the answers to the questions in homework 3.1.2d on electromotive force and internal resistance. So as always, the warm-up questions cover sort of basic concepts, ideas and definitions. So definitions for the following terms. For A, internal resistance is the resistance of a power supply or a source of electromotive force. Load resistance is the resistance of all of the circuit external to the power supply. Another way of thinking about it would be the resistance of all of the components between the terminals of the power supply, so across the terminals of the power supply. Electromotive force is the same definition as potential difference, but with a slight caveat. It's energy transferred per coulomb of charge to the charge carriers in a circuit, and that energy comes from an external source, a battery, a dynamo, etc., etc. And then terminal potential difference is the energy transferred per coulomb of charge from the charge carriers of the circuit to other forms like an electrical component or resistor. So, for example, to heat in a regular resistor, to motion in a motor, to light in a light bulb. Similarities then and differences between EMF and potential difference. Similarities, there's a couple. Both of them essentially measure the same thing, which is energy transferred per coulomb of charge, per unit charge. Both of them have units of volts. Both of them are really describing transfers of energy. EMF is from other forms to electrical. Potential difference is from electrical to other forms. And so that's really the difference. The difference is EMF is energy per coulomb transferred into the circuit to the charge carriers, whereas PD is energy per coulomb transferred out of the circuit. Equation-wise, if you remember, we've got conservation of energy, so total energy in is equal to total energy out. And we can have energy out per coulomb of charge is V voltage for the load resistors, so that's I big R, and the equivalent for the internal resistance is I little r. So E equals IR plus I little r, or you could have I and then brackets R plus R. And then the EMF in terms of the terminal PD, internal resistance and the current, well, this here, I big R, is the terminal PD, so E equals V plus IR. On to the main questions then. To help us with question 1, we've got a graph of voltage on our y-axis, current on our x-axis. It's worth thinking about our equations. Okay, remember, equations often tell us about what's happening with graphs. So we've just come up with the equation that EMF, energy in per coulomb of charge to the circuit, is equal to V, the energy out per coulomb of charge at the external circuit, plus I little r, the energy out per coulomb of charge at the power supply. And we can rearrange that equation to give us V equals. We want it in the form V equals because V is on our y-axis, so to be in the form y equals mx plus c. And if we do that, we have V equals minus IR plus E. Let's not worry about that too much. I've written it slightly differently, simply so I've got that in the form y equals mx plus c. The current, is on my x-axis here. Now, once I've got that, I can then directly infer what my gradient represents and what my intercept represents for my graph. And so the gradient is the internal resistance, the EMF is the intercept. So, which of these is the smallest intercept? The one with the lowest intercept is C. Which one delivers the most electrical power at a current of 1 amp? Well, power is current times voltage. So we've got the same current, so which is the greatest voltage at 1 amp? And that's going to be component or cell A. And then the smallest internal resistance is the one with the least gradient, so again that's going to be A. Question 2, I've got my circuit set up with my cell, my battery with an internal resistor, a variable resistor that I'm going to take different measurements for voltage across and current through. I'm going to plot up my graph and I need to work out the internal resistance. Essentially I need to find the gradient of my graph. So, to find my gradient I need to find out my change in y and my change in x. So change in y, I'll use a whole range of data. Remember, if I'm finding gradients I want to use as big a range of data as possible. So 6 minus 0.5 gives us 5.5 volts, and then my change in x is across a whole range of data 1.8 minus 0, so 1.8 amps, and then change in y, change in x is the gradient, V over I gives me 3.1 ohms. Question 3, I've got another circuit with a power supply of 1.55 volts EMF, an internal resistance of 0.4 ohms, an external load resistance of 5.8 ohms, and a current of 0.25 amps or 250 milliamps. And I'm asked to calculate the potential difference across the load. So I've got I, I've got R, I need to work out V. So very straightforward calculation. This V equals IR. So 250 times 10 to the minus 3, because it's milliamps, times 5.8 is 1.45 volts. And then I need to explain why the potential difference across load resistance is less than the EMF in the cell. Kind of a basic explanation. This, you have to keep coming back to this. It will come up quite often. So we're always losing energy at all points in our circuit, including in the power supply. So our answer is that some energy is used. You might see the term voltage dropped or voltage dropped as the charge passes through the power supply itself, and that's due to the resistance of the power supply. Part B, we've got this graph here, the cells left connected, and the graph shows how the current varies through time. And we are asked to describe how the current varies through time. Now, we're at A-level, not GCSE, so we're going to have to be really specific about this. The graph has numbers along the axes, and so if there are numbers of the graph, we can use numbers in our explanation. In fact, we're going to need to get the marks. So, the key point here is be specific with the values. So, first part of our description is that we've got a constant current of 250 milliamps for a time of up to about 10 hours. So, current remains constant at 250 milliamps between 0 and 10 hours, and then between about 10 and 11 hours, the current rapidly falls to 0 milliamps. So, being specific with the numbers in my answer to get myself full marks. For part 2, we're asked to suggest reasons why the current varies this way. So why is it constant for 10 hours? Why is it then dropped? So it's going to be constant current because there'll probably be a constant rate of reaction within the cell. So constant internal resistance as well, and that will last for the first 10 hours. That's why we would expect a constant current, because we wouldn't expect any changes to have occurred. Cells operate through chemical reactions. And then why does it drop off? Well, after 10 hours, the rate of reaction and therefore the EMF in the cell reduces. It might also be some change to the internal resistance as the chemical makeup of the cell changes, and so the current reduces, the current is less. We're then asked to use the graph in order to work out or estimate the total charge delivered by the cell. So this is the graph here. And what we need to do then is think about how we're going to find the total charge when we've got a graph of current against time. Now we know an equation that charge transferred is current times time, and actually if we're finding current times time here, what we're doing is we're finding the area under the graph. So we need to find the area under the graph, bearing in mind of course that on our x-axis time is in hours, not in seconds. We need to get into seconds in order to get consistent units. Okay, we also need our current in amps rather than milliamps. So if we zoom in, what we're essentially doing is finding the area of this. Now that's a little bit complicated if we're just going to be counting squares. I would suggest that perhaps the best way to do this is to break this up into two different parts. Essentially for the first 10 hours, what I've got is a square. So if I find the area of that square, that's the charge delivered in the first sort of 10 hours, and then between 10 and 11 hours what I've essentially got, to all intents and purposes, is a triangle. So if I find the area of that triangle, I'm then also going to be able to find the charge delivered in that last hour. So in order to work that one out, let's first of all have a look at finding the area of that square. So the area of the square is charge times time, so 0.25 amps times by 10 times 60 times 60 seconds is 9,000 coulombs, represented by this area here. And then area of a triangle is half times base times height, so half times by 0.25, that's the height, times 1 hour, 1 times 60 times 60. 60 seconds in a minute, 60 minutes in an hour, is about 450 coulombs. So my estimate there of the charge delivered is about 9,450, 9,500-ish coulombs. Very key point going forward. If you've got an equation which is one quantity is equal to one quantity times by another, you have a graph of those two quantities, we're usually finding the area under the graph. Again, units are important, if the prefixes or funky units such as hours or minutes or what have you. Question 4, kind of a basic, what's the difference between potential difference and electromotive force in terms of energy? So back to our original definitions, EMF, electromotive force, is the energy transferred to the charge carriers from an external source, power supply. Potential difference is the energy transferred away from the charge carriers to heat, to light, to motion, etc. at a resistor or component in an electric circuit. So it's the direction of energy transfer that's important here. Question 5, we've got some numbers that we need to deal with in order to work out the internal resistance of a cell. So we've got an EMF, we've got a value for the load resistance of 80 ohms, a current of 70 milliamps, and we need to find the internal resistance. We know epsilon, E, I, big R, and we need to find little r. The equation that we're going to use here is E equals I, R plus little r. If you remember this is energy transfer per coulomb charge into the circuit. I times big R is voltage V, which is energy transfer out of circuit per coulomb charge for the load resistors, and then I times little r is energy transfer per coulomb charge out the circuit at the power supply, conservation of energy. So rearrange that. If we divide both sides by the current, we get E over I equals R, big R plus little r. We want to find little r by itself, so we're going to rearrange that one simply to little r equals E over I minus big R. And now we can just plug in our numbers. So we've got 1.5 divided by 0.017, so that's 17 milliamps. Take away 80, it's something like 85 minus 80, or 88 minus 80 is 8.2 ohms. Question 6, we've got some symbols and we're going to do a little bit of algebra. We're interested now not just in EMF and current and resistance, but actually in power. So we're going to think back to our equations that we know for power. Power is equal to P is equal to I times V, is equal to I squared times R, and it's equal to V squared over R. And we're going to put those equations into the context, into the form of the things that we've been given here. So the power dissipated in the external resistance, big R, we need to give it in terms of E, R, I or R, is I squared times by R. The power dissipated due to the internal resistance is the same, I squared, but this time times by little r. And then the rate conversion of energy in the cell, now the rate of transfer of energy, that's power again. So what we're trying to find is the power converted in the cell, and that's I times V. Well, we don't have V in the cell, it's I times E. So we're looking at that sort of equivalency between potential difference and that we usually consider power of a resistor, and actually electromotive force, so the power of a power supply. So that's essentially rewording of P equals IB. So we then need to use those formulae to write down the equation expressing conservation of energy in the circuit, and then use that to show that I is equal to E over R plus R. Conservation of energy, what we're saying is energy in is equal to energy out, and actually energy per second in is equal to energy out per second. So power in is equal to sigma here, that's the total, so the total power out. Now the power is input only in one place, at the cell. So the power input at the cell I can give as I times E, and then power is delivered away from the circuit at two places. Mostly at the load resistor, so that's power given at a rate of I squared big R, and also at the internal resistor, so that's I squared little r. So what we've got there, in other words, is I times E is equal to I squared big R plus I squared little r. We can then work this through. There's a common term on all of these bits, which is I. So if we rearrange that, we would then get E equals I big R plus I little r. On the right hand side of the equation, I is the common factor, so we've got E equals I, then brackets R plus R, and then we simply divide down by the brackets to give ourselves I equals E over R plus R. It's a little bit of an exercise in algebra, this. But the key sort of jump that you've got to make, the key bit that you've got to sort of click with, is that these terms for power are equivalent to each other in terms of power in and power out. So this statement here is the really important one. We're then told that final statement tells us the internal resistance of a power supply limits the current which can be drawn from it. We need to explain why. So there's a couple of things here. first of all, the internal resistance of a cell, really we consider that to be a fixed value, right? We get a constant gradient when we're looking at those graphs of V against I that we came up with earlier in the homework. That means that the maximum current occurs when the total resistance, and so therefore actually the load resistance, is at its smallest value. So if the load resistance is essentially 0 or very, very small, we're going to have a very, very high current. We're not going to have an infinite current because the power supply itself has a fixed resistance, and so we're not going to have infinitely large current flowing. So when R is equal to 0, the internal resistance limits the current to a value of E over R. Right, the EMF divided by the internal resistance. That's the biggest current we're going to get in any circuit at any time. For the last part of question 6, we're told that a 5 kilovolt laboratory supply can be made safe for student use by connecting an internal series resistor. We've got different values of resistor available to us. Which of them would make the supply as safe as possible? Is it the one with 1 kilo ohm, 10 kilo ohms, 100 kilo ohms, or 1 mega ohm? We need to explain why. So, in order to make it as safe as possible, we need to make the current as low as possible. So in that case, what we need is as high an internal resistance as possible. So our value for our internal resistance is going to be the safest value is 1 mega ohm. If we've got a lower internal resistance, obviously a larger current is available to flow for the same value of EMF. Question 7, you've been asked a very, very similar question in one of the earlier homeworks that you've done, so we should be able to whiz through it. There's a bit of an extension difference at the end. There are actually 2 different questions asked on 2 different exams, so you can see there is a little bit of repetition in the bank of questions that people use. So learn as many of these past questions as you can. You may see something, if not exactly the same, then a little bit similar coming up in your exams in a couple of years. So, prefix n, nanoamps, is 10 to the minus 9, so m obviously doesn't mean times 10 to the minus 9, it means milli, or 10 to the minus 3, so you need 10 to the minus 3 for your answer there. You need to calculate a value for r, for reading 3. Remember, we're not going to forget those prefixes, so this time we're going to have 150 nanoamps, 74 millivolts. So R equals V over I, so 74 times 10 to the minus 3 divided by 150 times 10 to the minus 9 gives us 4.9 times 10 to the 5 ohms. To calculate the power being supplied in number 4, P equals IV, so 210 times 10 to the minus 9 times 57 times 10 to the minus 3. And get those numbers together, we've got 1.2 times 10 to the minus 8 watts. Okay, for part D then, we've got to take the data from the table on the other page, plot the points 1, 2 and 3, and then complete the graph. So that really means draw a line of best fit, and then from that we can predict the current that would flow from the cell if it was short-circuited. That is the current when R is reduced to 0. So let's have a look at, first of all, plotting those points. The points occur at 0, 1, 1, 0, 90, 83, 150, 74, where the first digit in each of those is the current in nanoamps and the second digit is volts. And if we plot those points, they occur something like that. And we can also plot a line of best fit then that goes through our graph something like that. So once we've done that, we then need to work out the current when this is short-circuited. So when it's short-circuited, when R is 0, the terminal potential voltage or terminal potential difference V will also be 0. There's no components for the charges to transfer energy at the external part, transfer energy at the external part of the circuit. And so what we're looking at here then is what's the current when the potential difference is 0. So our current there is about 430, 440 nanoamps, something like that. We then need to say what the experiment suggests for the value of the EMF of the cell, where the EMF of the cell is simply our y-intercept, and our y-intercept is something along the lines of 110 millivolts. There is a little bit of margin of error for each of those answers, 440 and 110, depending on how you've drawn your line of best fit. And then for the last part, we're asked to explain why the voltage across cell falls as the terminal potential difference is reduced. And what we're interested in here is that as R reduces, the load resistor takes up a lesser share of the total resistance of the circuit, when that total resistance is the sum of the load resistance and the internal resistance. And because it takes up less of the total share, it's going to have less of the total terminal sort of proportion of the EMF across the terminals and a greater proportion of the EMF across the internal resistors. We'll talk about that in a bit more detail as we come on to do potential dividers and some problems to do with sensors and circuits with components in series.